In this cubical box problem, we're looking at a box where we don't know the dimensions, but we know the diagonal that goes down the middle, catty corners, is 3. So I'm just going to pop out that little rectangle there. Let me see if I can get some straight lines, and let's do a little blue triangle. Whoops, that's way too fat. So let's do this triangle here. I'm going to just draw it over here so we can think of it in 2D. We're told that that diagonal is 3, and we don't know the sides, but it's a cube, so that backside must be x. But the diagonal that goes down the center, that one's kind of special. I'll draw that in the green line. Actually, I'll do red because it's special. So that's really our, what is that? I don't know, because it's not quite the side of a box. But can I get it from that 3 and that x? Well, I can't quite, but what I can do is look at this box again and look at this triangle that I'll do in green. Darker green so it doesn't look like the other sides. That green triangle and the blue triangle share a side. But I know all the sides of, well, I'm sorry, I don't know all the sides. I know 2 of the sides of the green triangle. The green triangle is isosceles. So x and x. So I know that's a 45-45 triangle. So I have this triangle. It's a right triangle because that corner is a right triangle. And this side of the triangle is a shared side with that the blue triangle. So the green and the blue triangles share that red side. Okay, but the green triangle, I can solve for that third side because I know it's a right triangle. I know this one's a right triangle too, by the way. And it's a special triangle because it's isosceles, which means these angles are each 45 degrees. So it's a 45-45, and my ratio for a 45-45 triangle to the legs of the hypotenuse is the leg times radical 2, gives me the hypotenuse. So now I know that red side is actually x radical 2. So I'm going to write that in red. Here, if I can just zoom in, x radical 2. There we go. So I know this one is x radical 2. Now I can find x because I have 3 sides of a triangle. So I can solve for x using the Pythagorean theorem. I'll use blue because I'm using the blue triangle now. So I have one leg squared plus the other leg squared equals the hypotenuse squared. So that's 9 equals x squared plus x squared, and radical 2 squared is 2. So combining my like terms, I have 2x squared plus x squared, so I get 3x squared equals 9, x squared equals 3, so x equals radical 3. All right, great. So this is radical 3 all the way around the box. So then my dimensions for part A then, there's 3 sides, so it's 3 inches. Don't forget your units, 3 inches, radical 3 inches, sorry. By radical 3 inches by radical 3 inches. So each side of the box is radical 3 inches. Okay, now to find the angle, theta, between the diagonal, that x radical 2. Oh no, I'm sorry, the blue one, the diagonal of the cube, the 3-inch one, and the lower corner of the box. So we're looking for this little angle right here, which is this guy in the blue triangle. And so I'm going to use that blue triangle again. And I can use any of these trig functions, right? Because I have all three sides. Because I know x equals radical 3. So I know this side equals radical 3 times radical 2, which is radical 6. So I can really use any of these functions. I'll go ahead and use sine just for fun. So sine of theta using SOHCAHTOA would be radical 3 over 3, which means my theta is sine inverse of radical 3 over 3. Alternatively, you can use cosine. You don't need to do all three of these, but just so that you see the answers that can match. So theta would equal cosine inverse of radical 6 over 3. And you can also use tan inverse. Tangent would be opposite over adjacent, so that's radical 3 over radical 6. All right, so I think we got all our answers now. The dimensions of the box are 3 by 3, radical 3 by radical 3 by radical 3. And the angle, I'll just pick one of these. And done.